Hey, this is Bloom and Glare, and today's tutorial is going to be covering how to create CG noodles or worms, any kind of gross, curvy, I guess, formerly hard to simulate objects, which with Houdini's new Vellum tools is actually really fun and easy to set up. So this is the result that we'll be after, something similar to this anyway. And you can see there's lots of geometry going on. I have the stretch ratio that's being shown here. So you're seeing how the noodles are being stretched as they collide with this kind of rotating box. And it's surprisingly simple to set up. I mean, this was really difficult just a few years ago to simulate, but again, with Vellum, it's kind of a breeze. So let's get started. Okay, so the first thing you want to do is open up Houdini and save the project. This is just a good habit to get into. I'm going to save it as Noodles, and I've done this tutorial a few times now, so I'm just going to overwrite. And the first step is to open up the geometry node, dive in, and we're going to be using the Vellum shelf tools, and in particular Vellum hair. And what Vellum hair uses as simulation objects are primitives, which is Houdini's terminology for curves or circles, splines, whatever they're called in other 3D software packages that you might be familiar with. But they're called primitives in Houdini, I think. So that's what we're going to be using. And in particular, we're going to be using this one, L system. And you can use the shelf tools, but sometimes it's just easier to bring them up like this. Again, I just hit tab and typed L system, and it creates this branch-like primitive. And if you want to see what's going on with primitives, one of the kind of easy ways to visualize whether or not you're going to have a simulatable object, I guess, or a simulatable primitive, is to look at the number of points that are distributed across the curve. So we have an even distribution of points, it seems, but there's not many of them, and they're also connected here at these branches. So we want to both disconnect them and then have a lot more points. So with a resample node, you can do that effectively and easily. Okay, so right off the bat, just by plugging it in, you can see that they are disconnected or unwelded. And this is going to be great for us because it means that we can simulate this, this primitive, and instead of having one mass, you're going to have a large number of disconnected curves, which will appear more noodle-like, I guess, once they're simulated. And we also want the points to be distributed at a greater number, and just so we get a more high quality simulation. Otherwise the curves are going to be very rigid, and if that's what you're going for, that's cool, but we're just going to try to get as close to noodles, I guess, as possible. So instead of using 0.1, I'm just going to go 0.01, and you can see that we've got a lot more points distributed across the curve. Okay, I'm going to turn this off for now and create a null called noodle out. And that's basically the entire setup for our simulated object anyway. And I'm going to title this noodle. Then using the shelf tools with this selected, we're going to hit Vellum hair. Okay, and it's just going to think for a second. Okay, I'm just going to close that. Now, automatically you're brought directly into the Autodot network, so you can start toying around with the simulation, and that's fine. We can do that automatically. And if we just hit play, I'm going to enable real-time firstly. What's going to happen is there's nothing for this to collide to, so it's just going to drop completely out of the scene. We do have gravity, which you can change if you'd like. For now, I'm just going to leave it as is. and I'll hit play, and you can see what's going to happen. So it simulates quickly, but again, there's no collider, so there's nothing for these noodles to collide to. So how do we do that? Well, there's a couple of different ways. You can create custom geometry like a box, or maybe a torus, or anything you'd like. I think I'll probably create a, I guess a torus. So I'm going to make a new node called geometry. Just call this torus. You can create a torus using the shelf tools, but it's just great to get in the habit of doing things custom in Houdini. At least it was for me when I started to learn, and I'm still learning every day. Okay, so we're going to create a torus, and it's a little bit large for what we're looking for. I mean, we can scale it here, or we can just bring down the radius, let's say 0.25 and 0.1, and I think that's a little bit better for what we're after. Let's dial up the fidelity of this just so we have a higher quality looking torus. I'll probably use something like 50 and 50. Okay, that's looking pretty smooth, pretty nice. And we'll make another null and just call that torus out. Okay, enable that. And let's just move it up a little bit. So probably about there, around the 0.5 mark in Y. You can also just type that in, whatever's easier. Okay, so when you use the Vellum shelf tools, like I was saying, there are two nodes that are created right off the bat. And one is your dot network, which is where everything is being simulated. That's where your Vellum solver is found. And there's an additional one called hair Vellum. And this is a node where your simulated geometry is being imported, and then your constraints, your Vellum constraints, are being imported. You can cache those. So once they're completely, once you're kind of happy with your simulation, you can come in here and define a geometry file, save to disk, and then you have access to that geometry file, and there's no more simulating involved. You can just basically take your geometry and start to play around with it, add color, which we can do. And this additional node, Vellum post process, it's typically a little bit more useful for things like Vellum soft bodies when you have not so high fidelity geometry to work with, and you can smooth out both the simulation and the geometry itself. There's a couple of subdivision options here, either loop or Catmull Clark. There's also this visualization tab which shows the thickness of what's going on. So if I zoom in here, you can see that this is actually the collision thickness of our spline, which is way thicker than the spline itself, obviously. So this is kind of what the output geometry is being calculated as in terms of its overall thickness when it's colliding with its colliding objects, whether that be ground plane or torus, what have you. And again, it's just really great to have these visualization nodes so you can come in and see what's going on after the simulation is complete. So there's also visualizations for stretch ratio, stretch distance, and these are options, or I guess parameters, that are available to you in the Vellum constraints, which are created inside our original, let's just hit L, which are created when we use the shelf tool. So if I come in here, you can see we have primitives that are being used, and they have these kind of default values of stiffness, damping ratio, bend stiffness and damping ratio. And these are just like dynamic constraints that you can play with, and if you want something to bend or stretch a lot more, then you can just dial this down. We're just going to leave these as default for now and see what we get. So let's move our noodle up a bit to maybe 1.333, and maybe that's too high. Let's go 1. Okay. And let's zoom in here and hit play and see what we're working with. And nothing's happening. So why is that? Well, that's happening because we haven't actually defined the torus as a collision object yet. And the easiest way to do that, I mean, there are a few different ways. One is you can come in here and create a static object and then define the object's path. An easier way, something that's a lot easier to set up, is just to use the shelf tools, go over here to collisions and define it as a static object or a surface collider. Vellum has surface collider automatically in its shelf tools, so let's just use that. And that should have been created, and it has. So let's hit L. So what's been brought in here is the torus as a colliding body or a colliding object, a static solver to solve the collision, and we still have gravity and we still have an output. So I'm just going to come out and turn off this Vellum node that was created and go back into the auto.network, and let's just hit play. Okay, so we actually have a collision. And just to see that a little bit more clearly, I'm going to hit D on the keyboard. Sorry. And go to background and change this to dark. Okay, and then I'm going to turn the grid off. So this will be a little bit more spooky looking, but I think it'll be easier to tell what's going on. And instead of having 240 frames, along the timeline, I'm just going to calculate 120 just so it's a little bit faster. And you can see they kind of smash into the torus and then slide off. Okay, so I mean, we can leave it there and then just kind of go with that as a collision. And this is kind of a basic setup, but like we were saying before, you can see how you have this space here. And that's because of the calculated thickness of the primitive, which we talked about earlier with the visualization tabs in the Vellum node here. So you can see there's actually no space in between these spheres, which are showing the thickness, and the surface of the torus. But how do we add a thickness to these? Well, it's very easy using if you want to use polywire. And I've seen people use wireframe, but I actually find polywire works a lot better. And we'll just enable this. And off the bat, it's way too thick. So how do we figure out the actual thickness of the simulation? So we'll hop back, go into auto.network, and that can be found in the Vellum solver. So if you go to Vellum Solver Advanced, you'll see default thickness here. And by default, it's 0.01. So how do we link this thickness with the thickness of our polywire that we created? And it's really easy. You're just going to right click, go copy parameter, come back to your Vellum node, and in the wire radius, you're going to right click and go paste relative references. So now, if you change in the solver the default thickness size, this will update. And to demonstrate that, we'll just enable this, dive back in. Actually, we'll come out here, we'll pin this view, dive back in, and then in the auto.network, you can see this is the current thickness, which is demonstrating the thickness of the collision with these wires. So this is what is being simulated, this thickness scale, I guess. So let's change that to 0.025, to 5, and we get something a lot thinner, and I think something that's going to look a lot better once colliding. So we will press play, and yeah, it looks a lot more like spaghetti now, or noodles, what have you. And having these connected is great. I mean, it's really fast, and that way you can kind of visualize directly what's going on. Now, these are colliding a little bit too quickly, and they're also only dropping once. They have no color, and there's I guess there's just not enough friction here. Like, it seems like they're just slipping off completely, and we want them to stick a little bit more. Let's pretend that they're maybe starchy noodles. So in the Vellum solver, you can come back to common, and there are lots of different parameters to play with. So one of the ones that we want to play with that creates really awesome simulations is the time scale. So if we just play now, you can see it's dropping really quickly. If we change the time scale to 0.25, then this is going to be a quarter of the time it would have taken when at 1 to simulate. So it's going to take longer across the timeline here, but you're just going to get a nicer result. So I think we can go to 1/3 of the speed, and yeah, that looks a lot nicer to me. So one more time. Okay, yeah, cool. And let's just play that. Yep, that looks a lot better. Okay, so you might ask, how can we drop more than one of these? Now, there are, I think, a few different ways and a few different expressions to use. This is the source. So this is how these are being emitted and how often. Now, you can emit them only once on frame 1. You can change the frame. So let's say we want to emit on frame 10. Then, oops. $F equals 10. And now they'll emit on frame 10. That's if you want to specify, but I find this expression works really, really well. So what it's doing is it's taking into account the total length of the timeline, and then it's saying every 8% of the timeline, or I think it's every eight frames, sorry, we're going to simulate one of these to drop. So let's just try that. And we also have to change to continuous. And you can see now every 8 frames we're simulating. And this is going to be a lot more geometry, but it makes for a lot cooler of a result. Now, these are falling very regularly, so it doesn't really look natural when we play back. They're self-colliding, but we can kind of tell that this is a branch structure, which we don't really want. I mean, noodles aren't usually emitted from branches, so I'm just going to come back here, and we'll change this to maybe every 12 frames instead. And another thing that we have to do, since this this geometry falling looks so regular, one of the ways to kind of smooth it out, it does take longer to simulate, is to increase the number of substeps that we have. I mean, you're probably used to this if you've used Vellum before. I think a value of 6 is probably going to be fine. The higher you go, the higher quality your simulation is going to look, but it gets, computationally expensive the higher you go. So let's just press, and you can see there's a kind of a substantial slowdown here. So I'm just going to pause this and we'll see the result. Okay, so this is the current result, and you can see that there's not a lot of friction still, so we have to change that. And we have to change the overall emission, because these are emitting in the exact same space each time they're being emitted, which is currently every 12 frames. So, I mean, how do we change that? And there are a few ways, but one of my favorites is to use a sine expression. Okay, so let's come back on. Okay, let's press play and see what's happening from above. Okay, so you can see kind of this repeating pattern, and it's not very visually impressive. I mean, it looks like weird tree branches that are dropping down unless we get really close. So let's create an expression to emit these more irregularly. So what you want to do is come back into the Noodle node and drop in a transform. Okay, and that's going to reset our simulation, which is fine. Okay, so when animating objects via expression, there's obviously tons of different expressions to use. Some of those can be things like $F for frame times 2, let's say. Oops, that needs to be a capital. And we'll hit play. Let's just make sure that our simulation is being turned off. We'll hit play here and you'll see that, So every frame, this is rotating by 2 degrees. If you increase the degrees, it's going to increase the speed. And I mean, this is something that you can use if you're animating things like the collision geometry. It's a little bit of a headache, so I'm just gonna turn that off. And we will animate this geometry in a minute, but for now, I just want to have kind of like a easily controllable but kind of randomizable rotation of these as they're emitting the curves themselves. So I'm just going to stop this. And one of the ones that I really love actually to use is the following function. So we're just going to type sin for sine, parentheses, and then $F for frame. And we're going to, multiply that by 10, and then multiply that by 10 again. And let's just copy that, and we'll paste it into the other rotation tabs here, and we'll hit play. So you can see you're kind of getting this this sine wave that's being applied. And if you want a greater level of rotation in Y so that you get a bit more variation, then just increase the number here. And I think that's okay, but usually this value is all right. Okay, and let's just try 20 here. I think that's going to give us too much overlap, so let's go back to 10. I think that's a good enough value. So basically, every time these are emitted, they're going to be emitted in a way that is irregular. Well, there is irregularity because it's a sine wave, but it's going to look quite irregular when it's smacking into the collider here. So let's stop the timeline. Okay, and we'll dive back out, make sure that none of this is activated, and then we'll go to our auto.network again. And you'll see now when emitted, they are still being emitted every 12 frames. There will be a lot more irregularity. So let's hit play. And I'll just pause this and we'll see the end result in a minute. Okay, so let's hit play and see what the result looks like. You can see they're falling now a little bit more irregularly, and we still need to change a few things, like the friction is far too low. I don't think there's actually, it looks like there's a bit of friction, but not too much going on. And I'd like to add a little bit more variation in these dropping, just because I can kind of still tell that these are, branch-like structures. And one of the ways that you can do that, if you're familiar with pops anyway, I'm just going to pause this for now, is to drop down a pop wind and dial that in. Okay, so by default, the air resistance is too high. So what that means is this is the level, I guess, or the scale at which the wind is going to affect our noodles. And I'm going to put that at 0.1. And instead of adding a wind velocity force, whether it's in X or Y or Z, I'm just going to add a little bit of noise variation. And for the noise, I'll put 0.6. Okay, and again, I'll pause this and simulate, and we'll see what the end result looks like. Okay, so let's see what's going on. And now it looks like we're getting a lot more variation. They're falling a lot more naturally. I kind of like how they're colliding. There's still not really enough, I guess, friction for my liking, but that's fine. That's really easy to do. So we'll change that quickly by going into the Vellum solver and coming down to the friction. And what we want to do is just change this static threshold. So let's just put this at maybe 2. And again, I'm going to pause and simulate, and we'll see what the end result looks like. So I actually used the wrong parameter. It's dynamic scale that you want to use, and I think the default value is 0.2 maybe. I've changed it to 0.65, and it looks like we're getting better result. Some of the noodles are sticking just around here, and there's a lot more variation to what's happening. Okay, so the last few steps are to animate our collider, so we're getting more, dynamic animation overall, and then also to maybe thicken these up a little bit and to give them a color. And you can render those with Mantra if you're using the Apprentice version, or the third-party engine of your choice, render engine of your choice. I really love Redshift. I like Octane as well, but it's entirely up to you what you want to use. I'll provide, again, a non-commercial version of this scene file, as well as the initial scene file that I showed. And I'll probably, I guess, make a limited commercial version available as well. Okay, so the tutorial right now is almost at, I guess, a half an hour, so I'll try and be quick, and let's see how far we can take this. So if we want to animate the collider, there are a few steps to take, but they're not too much trouble. One of the first things that you're going to want to do is come into the tab, which we've named Torus, and let's create a transform node. Okay. Now, you can transform within the node itself, the collider node itself. But what that ends up doing is it actually takes a lot longer for Houdini to calculate when you, let's say, come in here and Let's say we're going to rotate this every, we're going to rotate 5 degrees maybe every frame. And let's just see what that looks like. Okay, so quite slow rotation, which will be nice for the animation. But this is more, I guess, computationally intensive for Houdini to calculate, or at least to solve. So that's one way to do it, but we're not going to use that method. What we're actually going to do is come out here, and in the transform tab, we'll be doing the transform here. So we can go every frame. We want a 5-degree rotation. Okay, and maybe we want to rotate in X as well. And let's just try that. What does that look like? Okay, so that seems, it's kind of a nice constant, movement. It's irregular. I don't like how it restarts, but if you wanted to get something that was loopable, then you could either use the sine wave, which we've used before, or you could just self-animate it. Let's turn off the rotation in Y. Okay, and we'll come out here and just create a new camera. Tie view to camera, so this locks our viewport here. And we'll just zoom in so we get a nice symmetrical kind of rotation here. All right, now we'll turn this off. Dive back into our AutoDock network. And we're going to need to relay that transform information to this static object. So since we're using just the torus node as a whole, we can use transforming geometry, which is set up by default. Press play, and you can see that it's already receiving that information. It's calculating really quickly, as opposed to if we calculated inside the node. And we should get a pretty cool result, I think. So I'll pause this again and then replay the animation. Okay, so let's see what this is looking like. We're getting this kind of tumbling, rotating, noodle tossing effect, which I think kind of demonstrates everything that you need to know about how to set these scene files up and how quickly the the simulation times really are. So I'm going to pause this, and the really great thing about Vellum in particular is that you can, once simulated, let's just turn this on. You can make changes, and you don't have to resimulate. So come down here, create a color node. I just want to see, some variation in color of these. And let's just middle mouse click to see what attributes we're working with. So we have patch names, p-scale, we have UVs, so you can add some textures to this. But for the purpose of the tutorial, I just want to see in the viewport what colors we can get. So I think I'm going to use velocity as an attribute to define changes in color, and it'll create a kind of interesting look. So if we just enable this and press play, you can see that automatically you just have a kind of a uniform color that's being applied. And I mean, that's fine. There's nothing, kind of There's nothing wrong with that. But what if we want to animate colors, or get something that's a bit more visually striking or interesting? So one of the ways to do that is to use an attribute to drive a ramp change in color. So I'm just going to select something that's, let's say we'll use this one. Okay, that's kind of a nice gradient. And let's go like dusty pink. That's kind of nice. Okay, and we need to enter some information here. So if we are just playing, then all of these are going to be blue, which is fine, but it's not really what we're after. So let's pin this so we can see our torus. We don't want to see through it. So again, we're going to use velocity, as the attribute to drive these, and automatically you can see this change in color. So when the velocity kind of taps out, I mean, right now the range is from 0 to 1. You can change this as you see fit, but we're getting a nice variation of color here, which is, I think, pretty beautiful. Okay. And again, if we wanted to change the scale of the thickness of these, we could. Again, it's obviously all parametric, and even if you wanted to change the amount of these that are being emitted, you can, and the simulation time is very quick and easy to set up. So let's just see what this is looking like in mplay, and we'll go to effects. We'll add some motion blur, just from camera, I guess. And let's just start this. And I'm going to pause this. Okay, so the mplay animation is good to go, and let's just see what we're working with. So you can see the motion blur really helps with the animation, and yeah, I think that's something that you can use as a digital asset in the future to, maybe you're working in CGI for food, or even for something like visual effects for worms, what have you. This is definitely a handy, simple setup to use. Okay, so I've recently started doing tutorials, and hopefully this one works. I'd really appreciate it if you guys just commented, let me know what can be improved. I'm working with limited technology here, but hopefully this channel is something that can grow out of the use of tutorials, and also some of the personal projects that I've been working on. I have been working on a Blade Runner project for the past year and a half. It's almost complete, and I'd really appreciate if you guys could take a look at my channel and give some constructive criticism on how can I improve my work and videos moving forward. So thank you very much, and hopefully this has been a help to you. Again, feel free to contact me and let me know if there's something that you'd like me to cover. I am somewhat of a novice with Houdini, but I've really enjoyed the past year or so of picking it up and seeing what it's capable of achieving. So thanks again, and hope to talk to you soon.